Alright, this is concept F for regions. This is your last concept in Unit 2. Honors, you have one more. We're going to focus on something called calorimetry and using a formula to calculate some heat-related problems. So our main goal is by the end of this lesson and 2 days in class, you should be able to solve heat calculations for the various variables involved, which include heat, mass, something called specific heat, and then also a change in temperature. So we've talked a little bit about heat in the previous concept. Heat can't be measured directly and can only measure as it is transferred and changed into kinetic energy. So calorimetry is this process for the measurement of heat into or out of a system. Now we use joules, sometimes it could be in kilojoules, and some people use calories. We'll be using joules. There is a relationship between joules and calories though that you should be aware of, that 4.18 joules is equal to 1 calorie. So this is an example of a type of calorimeter, which is a device to measure the absorption or release of thermal energy. This indirectly measures the energy change between potential and kinetic energy by measuring the temperature change that occurs on water that's in the calorimeter. So the actual process takes place where letter A is, and then because that's going to either release heat into the water, which is B, or absorb heat from the water, we can then measure the temperature change and do some calculations related to it. So just keep in mind the law of conservation of energy, that the amount of energy released by a process must be equal to the amount absorbed by the rest of the system or surroundings. So if heat is lost by the system, that exact amount of heat should be gained by the surroundings. Or if heat is gained by the system, then that has to be exactly equal to the heat lost by the surroundings. In a lab where we don't have great systems or great calorimeters, we're going to see that that gets affected. But it has to be somewhere, we're just not able to measure it. In a calorimeter, the water is the surroundings and the sample is the system. So when the water's temperature increases, which is the surroundings, it means the sample actually lost energy and gave it off to the water. When the temperature of the water decreases, this means that A, or where the sample is, actually gained the energy or absorbed it from the water. So just kind of keep that in mind in terms of exothermic and endothermic processes. So the amount of heat gained or lost in a physical or chemical process can be calculated using the following equation, which is on the back of your reference table. So Q equals mc delta T. Q being the amount of heat that's absorbed or released, which is shown by a positive or negative value. M is mass, C is a specific heat value, and then delta T is a change in temperature. I would definitely make sure you write this part down, that the change in temperature is your final temperature minus your initial temperature. Now, heat capacity is a term that you should be aware of. It's the amount of heat needed to increase the temperature of an object exactly 1 degree Celsius. Because it's the entire object, this depends on both the object's mass and its chemical composition. So if I have 100 grams of air and water, they have different heat capacities. So it's going to take 101 joules to increase the temperature of air 1 degree Celsius, but it's going to take 41.79 joules to do this to water. Alright, so the specific heat capacity is the amount of heat it takes to raise the temperature of 1 gram of the substance by 1 degree Celsius. So this is what we use in our calculations because it's going to be a constant value for the substance. The lower the specific heat value, the more readily it will change temperature as it absorbs or releases energy. So again, the lower the specific heat, the more quickly it will change temperature. So again, keeping this in mind, we have air, which has a specific heat of 1.01 joules per grams degree Celsius, then water has one that will round up to 4.18. So based on that, we can keep in mind that air is going to change temperature much quicker than water. So that's why if it's been a really hot day, the sun has been out at night, the air feels much cooler if the temperature has gone down, but the water seems to not have changed at all. Your pool water or the lake, and that's because water has a much greater specific heat value. So Q equals mc delta T is used to calculate these heat-related problems when there has been a change in temperature. When we get into phases, honors, we're going to do this in the next concept. Regions, this will happen later in the year. We're going to see that there can be processes that happen without a temperature change, and we can't use this formula. But when we do have a temperature change, we can use this formula. So here's an example. We have aluminum. we're given the specific heat, we're given the mass, and we're also given the final and initial temperatures. And we're going to try and figure out the Q value, or for heat. So here I have T2, my final temperature, minus T1, my initial temperature. So I have a negative temperature change. This would tell us that there's been a loss of heat, so we should see a negative value for Q, or for heat. So I write down my formula. It's already been solved for the missing variable Q. I input the values, showing all the significant figures present, and then I solve, and then I'm going to round. Because we're multiplying, I need 3 significant figures, and I place this line over the 0 to show that that place value is significant, so I have 3. And you can see the negative Q value due to loss of heat. All right, here's another example where here I'm going to be looking for mass. I've been giving all of the other variables here, and you can see that in this case, we're not given the initial or final temperature, we're actually given the temperature change when it tells us how much it's increased by. So I'm going to go ahead, I'm going to rearrange for mass, as you can see here, and then I'm going to plug in my values as they were given, including all significant figures that were present, and I'm going to go ahead and multiply and divide, get my answer, which is positive, which matches the increase in temperature, and then round to 3 significant figures in this case because that's my lowest amount of sig figs there. And that would be the mass of the sample of water. Alright, so here you're going to practice on your own. So go ahead, pause the video, see if you can identify variables and set up the equation. So you should have gotten here that your mass, your specific heat, and then also your change in temperature, which was positive, and you're searching for your Q, or heat value. So you should have written it down, plugged in the given values, and then finally rounded it to 2,570, so it had 3 significant figures, and also included joules as your unit for heat. Okay, so tomorrow we're going to work, and actually really the next 2 days with regions, we're going to work on these problems, how to identify variables, how to solve for different variables, so make sure you bring any questions you have because we'll start off with this first thing tomorrow.